In the solar system, there is a planet. For years, we thought it was a boring, pale blue marble, a featureless, quiet world. We were wrong. So, very wrong. The 5.5-hour glance from a single spacecraft, sent in 1986, led to a 40-year lie. Because, beneath that seemingly calm surface, lies a chaos that defies the laws of physics. It spins on its side, tilted at an unbelievable 98 degrees, causing one pole to remain in pitch-black darkness for 21 years. Its magnetic field erupts not from where it should, but from a point shifted thousands of kilometers from its center. But the most unsettling part is that we don't even know what this planet is made of. If you love the thrill of unlearning what you know and starting from scratch, hit the like button and subscribe, because everything you believe is about to be shaken. Are you ready? Let's begin. For years, we knew it only as a punchline. It was the most ridiculed, most overlooked planet in the solar system. Whenever its name was mentioned, a part of our brain would automatically shut down the conversation. It was a choice, almost a reflex. But this ridicule was actually hiding a colossal truth. So, we turned our attention to the red deserts of Mars, the storms of Jupiter, or the rings of Saturn. And for that very reason, we completely missed the strangest, most alien world in our own backyard. We now understand that behind that simple joke was a veil of mystery that questions everything we know about planets. Because this condescension created a massive blind spot in our minds. For a moment, think about the other planets. Mention Mars, and you think of rovers, red dust, sunsets that paint the sky blue. Jupiter comes to mind with its great red spot, its radiation belts, its moon with a subsurface ocean, Saturn's rings, its hexagonal storm at the pole, its moon, Titan covered in methane lakes are iconic. But when we say Uranus, nothing more than a faint blue circle appears in our minds, a drawing in a textbook, a world where the only thing known about it, axial, is that it's tilted on its side. That's why there's no cultural weight attached to Uranus. There is no blockbuster movie set in its orbit. There is no famous image, like the rings of Saturn, seared into the public consciousness. This lack of attention is what prevented us from realizing what we were ignoring. But what's truly interesting is just how big this blind spot was. What was it that we were actually overlooking? Uranus is not small. It is not some fringe world. It was never a frozen pebble drifting in the outer darkness. The truth is, Uranus is the third largest planet in the solar system by diameter. It's about 4 times wider than Earth. If we could hollow it out, you could fit exactly 63 Earths inside. Its mass is more than 14 times the mass of Earth. It has a ring system. It has 29 known moons as of 2025. It has an atmosphere, a magnetosphere, weather, seasons, and an internal structure that scientists are still debating in peer-reviewed journals right now. It is, in every sense, a giant planet. But, in humanity's hierarchy of attention, it ranks below objects that are a fraction of its own size. One reason for this is distance. Uranus orbits the Sun at about 2.9 billion kilometers, shakesites 19 times the distance of the Earth. At that range, it takes light from our star about 2 hours and 40 minutes to reach it. It is therefore invisible to the naked eye under most conditions. So how did such a massive planet escape anyone's notice for most of history? Because For almost all of recorded history, nobody knew it was there until the night of March 13th, 1781. A man named William Herschel was systematically scanning the sky from his garden in England. Herschel was not a professional astronomer. He was a musician. But he had developed an obsessive interest in building telescopes, grinding his own mirrors, and cataloguing the stars. That night, he noticed an object that did not behave like a star. It showed a visible disk instead of a point of light, and on subsequent nights, it moved against the background of fixed stars. He initially reported it as a comet. But when other astronomers tracked its orbit and did the math, they reached a conclusion that stunned the scientific world. This was not a comet, it was a planet, a new planet, the first planet ever discovered in recorded human history. The weight of that sentence is often overlooked. Every planet known before that night, Mercury, Venus, Mars, Jupiter, and Saturn, had been visible in the sky since before humans invented writing. For thousands of years, from Babylon to Greece, from the Islamic Golden Age to Renaissance Europe. The number of planets was fixed, 5 wandering stars. The discovery of Uranus shattered that assumption overnight. It wasn't just the addition of a 7th planet to the list. It was the realization that the list had never been complete. It was the understanding that the solar system was bigger than humanity had known for its entire history. This discovery opened a door that could never be closed. Within decades, Hughes astronomers would find the first asteroids, then Neptune, then Pluto and the Kuiper Belt. Herschel proposed naming the planet after King George III to curry favour with the crown, Taschekinch. But the name didn't stick outside of Britain. It was the German astronomer Johann Bode who suggested the name Uranus, the father of Saturn and the god of the sky in classical mythology, and the name was internationally adopted. But each is what came after this discovery was a disappointment nobody expected, because when humanity got its first and only close-up look, what it saw was an almost featureless, much pale blue orb. When the Voyager 2 spacecraft arrived in the Uranian system on January 24th, 1986, the images it sent back were a complete letdown. There were almost no cloud bands, no visible storms, none of the swirling vortices that make Jupiter and Saturn a riot of color. The question on everyone's mind was this massive, historic planet really this boring? Was there nothing beneath that smooth exterior? But that single visual impression would lay the foundation for decades of misconception, because that smooth appearance was not a permanent feature of the planet. It was just a seasonal artifact. Voyager 2 arrived at Uranus during its southern summer solstice. This was a moment when one pole was pointed almost directly at the sun, and the other was facing deep space. The atmospheric circulation pattern at the solstice is completely different from how it is at other points in the planet's orbit. Scientists at the time didn't fully understand this. The visual blandness was real. But it was a snapshot of a particular moment in an 84-year cycle, not a portrait of how Uranus always looked. And as the planet progressed toward its equinox in 2007, ground-based telescopes and the Hubble Space Telescope began to detect cloud bands, bright storm features, nastasis, and atmospheric activity that had been almost entirely absent during the Voyager era. The planet had woken up, or rather, the geometry of the sunlight hitting its atmosphere had changed enough to alter the circulation patterns and make previously invisible structures detectable. Uranus had weather all along. It just wasn't performing for the camera when humanity stopped by for one afternoon. And this is a recurring theme with Uranus, because almost everything we know about this planet is based on a catastrophically small dataset. One flyby, a few hours of close observation, a snapshot taken under conditions we now know to be atypical, and from this tiny sliver of evidence, an entire planet was labelled boring. Consider what we've sent to other worlds. Mars has been visited by numerous orbiters, LaCroix landers, Bosch, and rovers over decades. Jupiter has been studied by Pioneer, Voyager, Galileo, Juno, and soon the Europa Clipper. Saturn was orbited for 13 years by the Cassini mission, which returned hundreds of thousands of images and transformed our understanding of the ringed giant and its moons. But Uranus got 5.5 hours. That's it. 5.5 hours of close-up data from a spacecraft designed in the 1970s. Launched in 1977. With instruments less powerful than what's in a modern smartphone. The situation is even more stark than that, because even those limited instruments revealed a planet so physically strange that it challenged fundamental assumptions about how giant planets work. Every time a better instrument is pointed at Uranus, something unexpected emerges. Not small anomalies, not minor deviations from predictions, but fundamental surprises that force scientists to revise what they thought they understood. The James Webb Space Telescope has observed Uranus multiple times since it became operational, and every observation has produced results that deepen the mystery. In February 2025, a Webb survey discovered a previously unknown moon in orbit around the planet, a tiny object about 10 kilometers in diameter that Voyager 2 had missed entirely, bringing the known moon count to 29. In 2025 and 2026, Webb mapped the vertical structure of Uranus's ionosphere for the first time in history, revealing temperature peaks, ion density profiles, and auroral features that did not match the predictions of existing models. The planet's upper atmosphere has been cooling for decades, and no one is entirely sure why. These discoveries, with every new look, drive home just how little we know. And in a separate study published in late 2025, reanalyzed Voyager 2 radiation data and concluded that the spacecraft likely arrived at Uranus during a rare and intense solar wind event, one that temporarily supercharged the planet's radiation belts to levels far higher than it normally sustains. This means one of the most dramatic measurements from our only close encounter was likely not representative of the planet's typical state. We caught Uranus on an unusual day, and for almost 40 years, we've been interpreting that unusual day as the norm. Every new piece of data shakes our old assumptions. But the layers of this planet resist easy understanding. Its atmosphere. When you actually study it instead of just glancing at a photo, contains hydrogen sulfide in its upper cloud decks, which means the clouds of Uranus literally smell like rotten eggs. This is chemically distinct from the ammonia-dominated upper clouds of Jupiter and Saturn. And this isn't a trivial detail. It's a compositional fingerprint that sets Uranus apart from its larger cousins. Its ring system, though much fainter than Saturn's, has its own peculiarities. The rings of Uranus weren't even discovered until 1977. That's when astronomers watching the planet pass in front of a distant star noticed the starlight briefly dimming just before and after the planet itself blocked it. The rings are narrow, dark, forked and separated by wide gaps. Their composition is different from Saturn's bright, icy rings. They're made of darker material and are thought to be geologically young. Webb has since imaged the rings in unprecedented detail, revealing structure and brightness variations that ground-based telescopes couldn't resolve. And its moons. The moons of Uranus are another underappreciated marvel. The 5 largest Miranda Ariel Umbriel Titania and Oberon were the primary targets for Voyager 2's cameras. Miranda in particular stunned scientists. But on this tiny frozen moon, there was a structure that upended everything we knew. Because this structure was among the tallest in the solar system. It couldn't be. It shouldn't be there. But there it was, right in front of us. Miranda is a tiny moon, only about 470 kilometers in diameter. Its surface looked as if it had been shattered and then reassembled. It featured giant cliff faces, some of the tallest in the solar system, cutting through terrains that inexplicably juxtaposed young and old geological features. The most dramatic of these cliff faces is a feature called Verona Rupes. It's estimated to be about 20 kilometers high. To put that number in perspective, the Grand Canyon is about 1.6 kilometers deep. The tallest sea cliffs on Earth, on the coast of the Hawaiian island of Molokai, reach about 900 meters. Verona Rupes dwarfs every vertical face on Earth by an order of magnitude. On a world with Miranda's weak gravity, an object dropped from the top of that cliff would take about 8 minutes to reach the bottom. Such an extreme and unexpected feature on a tiny frozen moon became one of the most reproduced images of the entire Voyager 2 mission. Because it proved that a world that should have been geologically uninteresting was one of the most visually stunning objects in the outer solar system. One theory suggested that Miranda was shattered by a cataclysmic impact and then gravitationally reassembled, its pieces coming back together in a haphazard jumble. But beyond this tiny frozen moon, beyond the rings, beyond the clouds, is the planet itself, the bulk of Uranus, the interior, the part we cannot see, cannot directly sample, and as of 2025, cannot even agree on what it's made of. For decades, Uranus and Neptune were classified as ice giants, a term used to distinguish them from the gas giants, Jupiter and Saturn. The idea was that while Jupiter and Saturn are mostly hydrogen and helium, Uranus and Neptune are dominated by heavier materials. Specifically, the ices of water, ammonia, and methane. But then in December 2025, a team from the University of Zurich published a study that pulled the rug out from under this entire framework. Using a new modeling approach, they showed that the available data is equally consistent with Uranus being rock-dominated rather than ice-dominated. This was a shock. The planet could be mostly water. It could be mostly rock. The current measurements cannot distinguish between these two fundamentally different possibilities. How could this be possible? It turns out the ice giant label was not so much wrong as it was unjustified. The researchers argued, we simply do not have enough information to know what Uranus is made of. At the most fundamental level, this is an extraordinary statement about a planet in our own solar system. We can characterize the atmospheres of worlds hundreds of light years away. Yet, but we cannot say whether the 7th planet from our own star is made primarily of ice or rock. This uncertainty is not a gap at the margins. It is a hole at the very heart of the problem. This is the planet most people have written off. This is the world met with ridicule and a shrug. A giant planet with 29 moons. A ring system. An atmosphere that smells of rotten eggs. Seasons that last for 2 decades. A magnetic field that comes out the side. And an interior that might be made of rock. Or exotic high-pressure ice, and no way of telling which. Everything described so far is just the surface layer of what makes Uranus strange. The truly bizarre features. The ones that stop planetary scientists mid-sentence, occult, lie deeper. They are about the tilt, not just the fact that Uranus is tilted, but what that tilt does to the planet's seasons, its magnetic geometry, its energy budget, and what it means to be a planet in an orderly solar system. Because Uranus isn't just tilted, it is lying almost completely on its side. And the consequences of this single fact ripple through every physical system the planet possesses, producing effects so bizarre they have no close parallel in any other world in our solar system. Every planet in the solar system is tilted. Earth is tilted about 23.5 degrees from the vertical. That modest angle is the reason seasons exist. Mars tilts by roughly 25 degrees. Saturn, about 27. Jupiter barely tilts at all. Just 3 degrees from the vertical. Neptune sits at about 28 degrees. Quite similar to Earth. These are normal numbers. The tilts of well-behaved planets. But Uranus tilts by about 98 degrees. It takes a moment for that number to sink in. This does not mean Uranus is just a bit more tilted than the others. It means Uranus has tilted past the vertical. Its axis does not point up. It does not point sideways. It points almost directly along its orbital plane, slightly past sideways. The planet doesn't spin like a top. It rolls like a ball. And the consequences of this geometry are so extreme, they transform almost every normal planetary process into something unrecognizable. For example, sunlight. Let's start with this most basic consequence. On a normally tilted planet, the equator receives the most consistent sunlight throughout the year. The poles receive less, the seasons change. But every part of the surface gets some sunlight and some darkness on a daily basis for most of the year. But on Uranus, at the solstice, one pole is staring almost directly at the sun. That pole and its surrounding hemisphere are bathed in decades of uninterrupted sunlight. Not days, not weeks, but decades. About 21 Earth years of continuous daylight for the sun-facing pole. Meanwhile, the opposite hemisphere is turned completely away from the sun. It remains in continuous darkness for that same 21 years. Not twilight, not filtered dim light. The sun is not visible above the horizon for an entire human generation. Then the planet moves on in its orbit. The geometry shifts, and as Uranus approaches its equinox, the sun moves toward the equatorial plane. And for a time, a more normal cycle of daylight briefly occurs over the entire planet. The equator sees the sun rise and set. The poles experience rapid transitions between light and dark in a brief window of its 84-year orbit. Uranus acts almost like a normal planet. But then the equinox passes, and the other pole begins its long turn toward the sun, and the entire pattern reverses. The hemisphere that was in darkness for 2 decades now enters 2 decades of light. The hemisphere that was bathed in sunlight is plunged into night, and the cycle continues, slow and relentless, with each season lasting longer than most human careers. This is not a trivial astronomical curiosity. This fundamentally changes how energy moves through the planet's atmosphere. On a normally tilted world, the equator is the primary driver of atmospheric circulation. It receives the most solar energy, heats up, fall, and drives convection patterns that transport heat toward the poles. But on Uranus, at the solstice, the pole receives more direct sunlight than the equator. The energy input is inverted relative to a normal planet. The hottest spot on the planet is not the equator. It's the pole facing the sun. Remarkably, however, temperature measurements show that Uranus's equator is not significantly colder than the sunny pole. Heat is being redistributed around the planet with extraordinary efficiency, by mechanisms that atmospheric scientists are still trying to fully explain. This redistribution is one of the quiet mysteries of Uranus. The naive expectation would be for the atmosphere to show enormous temperature contrasts between the sunny and dark hemispheres. But it doesn't. Something within the atmospheric circulation is smoothing out those differences. The timing of the Voyager 2 flyby becomes critical to understanding just how misunderstood the planet was. Voyager 2 arrived at Uranus during the southern summer solstice in January 1986. The South Pole was pointed almost directly at the Sun. The spacecraft approached from the sunlit side, meaning it saw the hemisphere that had been in continuous daylight for about 2 decades. That hemisphere, because it had been baked in continuous sunlight for 21 years without a day-night cycle to drive rapid convective changes, showed almost no visible cloud structure. The atmosphere appeared placid, upwards, smooth, dead. The conclusion reached at the time was understandable. Uranus looked like an atmospherically inactive planet. But that conclusion was wrong. It was wrong because it mistook a seasonal extreme for a permanent state. And as the years passed, and Uranus moved toward its equinox in 2007, the evidence began to mount. The first clues came from the Hubble Space Telescope in the late 1990s and early 2000s. Hubble's cameras began to detect faint banded structures in the upper atmosphere. Cloud features that had been invisible to Voyager started to emerge. As the planet neared equinox and the sun began to illuminate lower latitudes more directly, the changes accelerated. By 2004 and 2005, Hubble was recording transient bright cloud features at mid-latitudes that rivaled anything seen on Neptune. But the real revolution came with ground-based telescopes. The twin Keck telescopes in Hawaii were equipped with adaptive optics systems that compensated for the blurring effects of the atmosphere. And when Keck turned its instruments on Uranus in the years around equinox, the results stunned the community. The planet was covered in atmospheric activity. Bright convective cloud systems popped up at multiple latitudes. Dark spots, reminiscent of Neptune's great dark spot, but unique in their behavior, formed and dissipated on timescales of weeks to months. Banded cloud structures appeared in the deep atmosphere, visible at infrared wavelengths that peered deeper than visible light. The atmosphere of Uranus wasn't just active, it was dynamic in ways the Voyager data gave no reason to expect. The most remarkable event occurred in 2014, when an exceptionally bright storm complex erupted in the northern mid-latitudes. These storms were so large and so reflective that they were detected not just by professional observatories, but by amateur astronomers using their backyard telescopes. A cloud feature on a planet nearly 3 billion kilometers away, visible from a backyard telescope, is an extraordinary thing. It meant the storm was reflecting an enormous amount of sunlight from a cloud top that extended far above the surrounding haze. But beneath all this visual evidence lay an even deeper anomaly. In one of the planet's most fundamental properties, its heat balance. So beneath all this visual evidence lay an even deeper anomaly in one of the planet's most fundamental properties, its heat balance. Now, let's dig a little deeper, because this anomaly is fundamental to how wrong the planet is. Every other giant planet in the solar system, Jupiter, Saturn, and Neptune, radiates significantly more energy than it receives from the Sun. This excess energy comes from their interiors, a remnant of the heat from their formation, sustained by ongoing gravitational contraction, differentiation, or other internal processes, like an engine running in winter. These planets generate their own internal heat and radiate it into space. The numbers are striking. Jupiter radiates roughly 2 times the energy it absorbs. Saturn radiates about 1.8 times. Neptune, despite being the most distant giant, still radiates about 2.6 times the energy it receives. This seemed to be a fundamental rule of giant planet physics. But Uranus, when its energy budget was measured by Voyager, 2 tapas appeared to be radiating essentially no more than it absorbed. The ratio was indistinguishable from 1. This made Uranus unique among the giant planets. It appeared to have no internal heat source at all, as if the primordial heat from its formation had somehow been lost or locked away. To understand why this is so disturbing, you need to understand the relationship between Uranus and Neptune. These 2 planets are not just neighbors in the outer solar system, they are near twins. Neptune is slightly more massive, roughly 17 Earth masses compared to Uranus's 14. Neptune is slightly smaller in diameter, meaning it's a bit denser. But in terms of their gross physical properties, size, mass, location in the outer solar system, presumed origin from similar materials in similar regions of the protoplanetary disk, Uranus and Neptune are the most closely matched pair of planets in our entire system. They are more alike than any other pair. That is why planetary scientists routinely describe them as siblings. And every model of solar system formation predicts they should have formed under broadly comparable conditions and evolved along broadly comparable paths. But their thermal behavior is completely different. Neptune radiates roughly 2.6 times the energy it absorbs, while Uranus appeared to be radiating essentially nothing beyond what the Sun provides. This is not a small discrepancy. This is like measuring 2 houses built in the same year on the same street, out of the same materials in winter, and finding one is warm and the other is freezing cold inside. The first question any investigator would ask is not what's wrong with cold houses in general, but what is it about this specific house that the other one doesn't have? What event? What alteration? What structural difference explains why 2 nearly identical objects ended up in such different thermal states? This question has driven much of the theoretical work on Uranus's interior for the last 40 years. And the answer that consistently rises to the top of the list is the one thing that clearly separates Uranus from Neptune: the tilt. While Neptune tilts by a modest 28 degrees, Uranus tilts by 98 degrees. Whatever caused that tilt, whatever violence was responsible, is the most visible difference between the 2 siblings, and it might be the explanation for why one went thermally quiet, and the other did not. But This measurement was based on an assumption that had preoccupied scientists for nearly 4 decades. The assumption that Voyager's data was correct, and that assumption was not shaken until July 2025. A study led by researchers at the University of Houston presented a revised energy budget that covered a full orbital period from 1946 to 2030. By combining spacecraft observations with improved computer modeling of how Uranus absorbs and radiates energy at all latitudes and all seasons, they showed that the planet does radiate more heat than it absorbs, about 12 to 15% more. The internal heat flow was real. It was just very slight, much smaller than Neptune's, but it was there. This finding upended one of the oldest assumptions about the planet. Uranus wasn't thermally dead, it was thermally quiet. And that distinction matters immensely because it changes which internal models are viable and which are not. A planet with a small but detectable internal heat source is structurally different from a planet with no heat source at all. The insulating barrier hypothesis, for instance, is still plausible, but now it has to be recalibrated. The interior cannot be so perfectly insulated that no heat escapes. Something is getting through, just far less than in any comparable world. The Houston study also revealed something else directly tied to the tilt. Uranus's energy budget varies with its seasons. The amount of heat the planet absorbs changes significantly depending on which hemisphere is facing the Sun and how directly. Over an 84-year orbit, the total absorbed solar energy fluctuates in a pattern that reflects the extreme seasonal geometry. This means the atmosphere and the uppermost layers of the interior are constantly adjusting to an energy input that changes on decade-long timescales. A slow pulse of warmth and cold that has no parallel on any other giant planet. This connects to the giant impact hypothesis, the leading explanation for why Uranus is tilted on its side. Because that impact may have shaped not just the angle of the axis, but the entire thermal evolution of the planet. So how exactly did this collision happen? And how did it change the planet's structure so fundamentally? Because, in the standard model of solar system formation, giant planets formed from the gas and dust in the protoplanetary disk surrounding the young Sun. Jupiter and Saturn accreted massive hydrogen and helium envelopes early on, when they could still gravitationally capture the lightest gases from the disk. Uranus and Neptune formed later, or in regions that were less gas-rich. Within this framework, there is nothing that naturally produces a 98-degree tilt. Planets forming from a disk of material all orbiting in roughly the same plane should spin in roughly the same direction, with their axes roughly perpendicular to that plane. But 98 degrees is not a small deviation. It's a catastrophe. The most widely accepted explanation is that a body roughly 1 to 3 times the mass of the Earth struck the young Uranus at a specific angle and velocity, knocking it on its side without completely destroying it. The timing of this impact is important. If it happened early enough, at Souths, while Uranus was still accreting its atmosphere, the atmosphere would have had time to settle into the new rotational frame. But some models suggest the impact could have also created a debris disk around the tilted planet, from which some of the inner moons later formed. This leads us to direct evidence. The 5 major moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, all orbit in the planet's equatorial plane, at the same extreme angle as Uranus itself. Their orbital plane follows the tilt, not the reference frame of the solar system. This alignment is one of the strongest pieces of evidence that the moons formed after the tilting event. If they had existed before the impact, their orbits would have been disrupted. But their current state suggests they condensed from a disk of material produced or reordered by the impact itself, and Miranda's tortured surface fits this narrative. If Miranda formed from impact debris, it may have emerged as a world with a heterogeneous interior, prone to uneven geological evolution. But there are other possibilities besides this single, massive impact scenario. Perhaps it wasn't a single blow, but a series of smaller impacts. In this scenario, no one event was responsible. Instead, a sequence of collisions, each one contributing a fraction of the total tilt, gradually pushed the axis further and further from the vertical. This model avoids some of the fine-tuning problems of the single impact scenario. But an even newer third class of models suggests that gravitational interactions with other planets during their orbital migration could have contributed to or even dominated the tilting process. In these scenarios, the giant planets did not form in their current orbits, but migrated inward and outward in the young solar system, exchanging angular momentum and passing through orbital resonances that could have potentially triggered large tilts. The scientifically honest picture is that we don't know which of these scenarios is correct. But the tilt itself, as extraordinary as it is, doesn't fully capture what makes Uranus so strange. The tilt is the seed. The weirdness grows from it in all directions, into the seasons, the energy balance, the atmospheric circulation, and into something even harder to explain, the magnetic field. Because when Voyager 2 measured Uranus's magnetic field, what it found was so far from any prediction that it forced a complete rethinking of how planetary magnetic fields are generated. On every well-studied planet in the solar system with a global magnetic field, the field behaves in a geometrically sensible way. The magnetic poles are located near the rotational poles. The field is roughly symmetric, curving in clean lines from one pole to the other, similar to the pattern you get when you sprinkle iron filings around a bar magnet. The axis of the magnetic field is slightly tilted from the rotation axis, but that tilt is small. On Earth, the magnetic pole is about 11 degrees away from the geographic pole. On Jupiter, that offset is roughly 10 degrees. On Saturn, the alignment is nearly perfect. Less than 1 degree of separation. This is not a coincidence. This is a consequence of how planetary magnetic fields are generated. Deep inside, electrically conducting fluids. Liquid iron on Earth, metallic hydrogen on Jupiter and Saturn, are stirred by convection and the planet's rotation. The rotation organizes the flow into patterns aligned with the spin axis. And because these fluid motions generate the magnetic field through a process called the dynamo mechanism, the resulting field is naturally aligned with the rotation. It's one of the cleanest, most intuitive relationships in planetary physics. But then there's Uranus. When Voyager 2 measured the magnetic field of Uranus in January 1986, the data defied every expectation the science team was prepared for. The magnetic axis was tilted by 59 degrees from the rotation axis. Not 11 degrees like Earth, not 10 degrees like Jupiter, but 59 degrees. The magnetic poles were closer to the equator than they were to the geographic poles. The field did not emerge symmetrically from the planet's center. It was displaced Halsey's offset from the middle of the planet by about 1/3 of the way to the surface. And the shape of the field was not a clean dipole. It was messy, with strong, higher-order components that gave the field a lumpy, asymmetric geometry unseen on any other planet. At first, scientists thought the measurement might be anomalous. But the data were consistent across multiple instruments, and the flyby geometry was well understood. The measurement was solid. 3 years later, Voyager 2 reached Neptune and found something similar. Neptune's magnetic field was also severely tilted, by about 47 degrees from its rotation axis, and offset from the planet's center by a similar amount. This was confirmation that the Uranus measurement was not a fluke. The ice giants, which, as a class, Yapaks, had rule-breaking magnetic fields. This dual result ruled out one of the earliest proposed explanations for Uranus's magnetic weirdness, that the field was in the middle of a polar reversal. The fact that Neptune showed the same pattern made the reversal explanation impossibly unlikely. Because the odds of catching both planets in the middle of a reversal during the same 10-year mission were infinitesimally small. The most accepted explanation over the last 3 decades is structural. On Earth, the magnetic field is generated deep inside, in the core. On Jupiter and Saturn, the dynamo operates in the deep interior, where hydrogen is compressed into a metallic state. In both cases, the dynamo region is centered on the planet's core and is roughly symmetric about the rotation axis. But on Uranus and Neptune, the dynamo is thought to operate not in the deep core, but in a shallow shell. The conducting fluid is not metallic hydrogen or liquid iron. It's formed by water, ammonia, and other volatile compounds being compressed at high pressures into an electrically conducting state. A state sometimes called ionic water or superionic ice. This conducting layer sits on top of the rocky or mixed composition core and below the hydrogen-helium envelope. If the dynamo operates in a thin shell rather than a deep sphere centered on the planet's core, the geometry of the resulting field changes dramatically. A thin shell dynamo naturally produces fields that are offset from the center, have strong, higher-order multipole components, and can be tilted at large angles from the rotation axis. The models are not yet refined enough to reproduce the observed field of Uranus in detail, but they capture its general character. This means Uranus's magnetic wrongness may not be a sign that something is broken, but a direct reflection of where the field is being generated inside the planet. But this explanation raises as many questions as it answers, and the evidence for how this complex structure interacts with the atmosphere has only just begun to emerge, in essence, with a new and powerful tool, the James Webb Space Telescope. And the evidence for how this complex structure interacts with the atmosphere has only just begun to emerge, with a new and powerful tool, the James Webb Space Telescope, axial. But now comes the truly incredible moment. This telescope was not just designed to look at distant galaxies. It was a key to unlocking one of the biggest mysteries in our own backyard. A key to the very heart of Uranus. And when that key turned the lock, what we saw fundamentally shook the scientific world. Because this telescope saw, for the first time in history, the fingerprints of the planet's magnetic field on its atmosphere. And those fingerprints looked like nothing we expected. This was the most concrete, most visual proof of the wrongness of Uranus. In 2025, Webb was used by a team led by Henrik Mellin of Northumbria University to observe Uranus's ionosphere. The charged upper layer of the atmosphere where the magnetic field leaves its mark. The ionosphere glows faintly in the near-infrared, shorts, emitting light from a molecule called HH, 3+, a positively charged form of hydrogen. This molecule is created when energetic particles from the magnetosphere or the solar wind collide with hydrogen in the upper atmosphere. By mapping the distribution and intensity of this emission across the planet's disk, the team could trace where the magnetic field was funneling energy into the atmosphere. And what they found was shocking. The emission was not concentrated at the geographic poles, Waukee as it would be on Earth or Jupiter. It appeared in equatorial and mid-latitude regions, consistent with the severely tilted magnetic field. This meant the magnetic poles were far from the rotational poles. This was a revolution. For the first time in history, scientists were seeing the direct effect of this bizarre magnetic field on the atmosphere. This wasn't a theoretical model. This was a real observation. And it proved just how extraordinary Uranus really is. The team detected auroral features in both the northern and southern hemispheres. But these aurorae were not where any intuition about planetary aurora would place them. On Earth, the northern lights appear in rings around the Arctic and Antarctic. On Uranus, the equivalent phenomenon crosses latitudes that would correspond to the tropics and temperate zones on Earth. For a moment, consider what this means. On Earth, aurora are a polar phenomenon. People travel to Iceland, Norway, or northern Canada to see them. But if Earth's magnetic field were configured like that of Uranus, the northern lights would be visible over Mexico City, Cairo, and New Delhi. The southern lights would shine over Sydney, Johannesburg, and Buenos Aires. The entire intuitive geography of the magnetic interaction between a planet and its space environment would be turned inside out. This is what Uranus lives with as a permanent state, not a temporary anomaly, but the fundamental way its magnetosphere interacts with the solar wind and its own atmosphere. It was the most striking example of just how different a planet could be. But this was only the beginning. The 2025 observations also revealed a dark band in the ionospheric emission that aligned with the magnetic dip equator, the line on the planet's surface where the magnetic field runs parallel to the ground. This was the first direct detection of the magnetic field's footprint on Uranus's ionosphere, and it confirmed that the tilted Hartrich-Schwarz offset field was not just a distant field phenomenon measurable from space. It was physically shaping the atmosphere, influencing where charged particles are deposited, where heating occurs, and where the upper atmosphere is ionized. A follow-up study published in February 2026 by Paola Tosi and colleagues took this even further. Using a 15-hour continuous observation session that covered almost a full rotation of the planet, they mapped the vertical structure of the ionosphere for the first time in history. They measured how the temperature and ion density changed with altitude, from the cloud tops up for thousands of kilometers into the thinning atmosphere. The results showed that temperatures peaked at 3,000 to 4,000 kilometers above the planet, while ion densities peaked much lower, near 1,000 kilometers. Both measurements were significantly different from what models had predicted. The ion densities were weaker than expected. The temperature structure was more complex, and this tied into a broader puzzle known as the giant planet energy crisis. on every giant planet observed so far, the upper atmosphere is significantly hotter than it should be based on solar heating alone. The Sun doesn't provide enough energy to the upper atmospheres of these distant worlds to explain the temperatures measured there. An additional energy source is heating them from below or within. And on most giant planets, the main suspects are gravity waves propagating up from the lower atmosphere and auroral heating from the magnetosphere. But on Uranus, the mystery is compounded by the planet's unique magnetic geometry. The auroral energy is deposited at low and mid-latitudes instead of the poles, meaning the heating pattern is fundamentally different than on any other giant planet. And yet, the upper atmosphere still shows elevated temperatures. Whatever mechanism solves the energy crisis for Jupiter and Saturn may not be directly applicable to Uranus, because the geometry of the energy input is so different. This meant the planet wasn't just working differently on the outside, but on the inside as well. And one of the biggest clues to that internal structure lay in one of the most fundamental questions. What was Uranus made of? This question should have seemed answered decades ago. We know what Earth is made of. We know the broad composition of Jupiter and Saturn. But Uranus, despite being one of the 8 major planets in our own solar system, remains compositionally ambiguous at the most basic level. The conventional picture, established in the decades following the Voyager flyby, divided Uranus into 3 layers: an outer envelope of hydrogen and helium gas, a thick middle mantle of compressed ices, and a small rocky core at the center. This 3-layer model fit the available data well enough. The term ice giant was coined to describe this structure. But the available data was not as constraining as the confidence of the label implied. The primary observational inputs are the planet's total mass, its radius, its gravitational field as measured by its effect on the orbits of ring particles and moons, and its rotation rate. From these quantities, scientists can calculate how the density varies with depth and test which combinations of materials are consistent with the observed profile. The problem is, the solution is not unique. Very different interior compositions can produce the same mass dense, radius, and gravitational moments. And this degeneracy, to use the technical term, is the crux of the problem. And it's not a small degeneracy. As the December 2025 paper from Luca Mori and Professor Ravit Held at the University of Zurich showed, the range of possible interiors spans from models where water dominates the mantle to models where rock dominates. The rock-to-water mass ratio, consistent with the available data for Uranus, ranges from 0.04 to 3.92. That is a factor of almost 100 between the most water-rich and most rock-rich models. Let that range sink in for a moment. We're not talking about a 10% uncertainty. We are talking about a planet that could be almost entirely water beneath its hydrogen envelope, or almost entirely rock. And we currently cannot distinguish between those 2 fundamentally different objects. So, what does all this uncertainty, all this wrongness, mean when you put it all together? What final conclusion does all this evidence lead us to? Because the ultimate secret of Uranus is hidden in the final picture that combines all these pieces. And that picture is one that will change all our ideas of what a planet can be, because the ice giant label assumes an answer. But the data doesn't provide one. The Zurich team's approach was deliberately agnostic. instead of starting with a presumed composition and checking if it fit the data. They started with randomly generated density profiles and applied an iterative algorithm that converged on models that satisfied hydrostatic equilibrium, the observed gravitational moments, and thermodynamic consistency. The result was a vast landscape of valid solutions that spanned compositions, temperature profiles, and convective structures that previous models had ruled out by assumption rather than by evidence. This was a scientific revolution. It showed just how fragile even our most basic knowledge about a planet was, and this leads directly to the exotic states of matter inside Uranus. Because, deep inside this planet, states of matter may exist that have no analogue on the surface of Earth and are only now beginning to be recreated in laboratories. At the pressures found deep inside Uranus, water doesn't behave like water. It enters a state called superionic ice, in which the oxygen atoms are locked into a crystal lattice. But the hydrogen atoms move freely through the lattice like a liquid. The result is a material that is simultaneously a solid and a liquid. A crystal that conducts electricity because the hydrogen nuclei carry charge as they flow. This is not theoretical. Superionic ice has been created in laboratory experiments, most notably at the National Ignition Facility at Lawrence Livermore National Laboratory. Using laser-driven shock compression to replicate the pressures and temperatures inside ice giants, the experiments work by firing a series of powerful lasers at a small sample of water, compressing it to millions of times atmospheric pressure in a fraction of a second, and then measuring how the material responds. The results confirmed that at pressures greater than roughly 1 million times sea level atmospheric pressure, water transitions to the superionic state. The oxygen lattice forms. The hydrogen becomes mobile. The material becomes an electrical conductor. This was a landmark achievement in high-pressure physics. But it also deepened the mystery of what is actually happening inside Uranus. Because the conductive properties of superionic ice are different from those of liquid metallic hydrogen or liquid iron. It conducts electricity, but not in the same way or with the same efficiency. Its convective properties are different. In superionic ice, the oxygen lattice is fixed. Only the hydrogen moves. This means convection, in the traditional sense, may not happen at all within a superionic layer. Heat transport would happen by a different mechanism. If a significant portion of Uranus's interior is made of superionic water, it would create a region where heat is trapped, not because of a compositional barrier, but because of the physics of the material itself. The superionic layer would act as a thermal blanket, slowing the escape of primordial heat from the deep interior to the surface. This provides another possible explanation for Uranus's thermal quietness, one that does not require a giant impact to set up an insulating gradient. The material itself, under the conditions that exist inside the planet, is naturally insulating. But this story has a critical caveat. The lab experiments were done on pure water. The interior of Uranus, whatever its composition, is not made of pure water. It is a mixture. And when you add impurities to water under extreme pressure, the phase behavior changes. Every number carries an uncertainty. And if the interior is rock-dominated rather than ice-dominated, the superionic story may not apply at all. The conducting fluid would be something else entirely. Perhaps silicate material under extreme compression, and the dynamo mechanism would operate in a different region, at different depths, with a different geometry. The thermal insulation mechanism would be different. The density profile would be different. The entire physical picture of the planet's deep interior would change from the ground up. This is the heart of the problem with Uranus. We are not dealing with a single unknown. We are dealing with a cascade of unknowns, each one dependent on the others. The magnetic field depends on the interior structure. The interior structure depends on the composition. The composition depends on measurements we do not have. And until we get those measurements, every model of Uranus, every paper, every simulation, every textbook explanation is built on a foundation that could be fundamentally changed by a single, definitive observation. And this gap is not academic. It has consequences that extend far beyond a single planet. Because the composition of Uranus is a benchmark for understanding an entire class of worlds. Among the thousands of exoplanets discovered in the last 3 decades, the most common type of planet in the galaxy is not a gas giant like Jupiter or a rocky world like Earth. It's something in between. Sub-Neptune and super-Earth-sized planets, with radii roughly 2 to 4 times that of Earth, appear with a frequency that dwarfs all other categories of planets around other stars. They are the default planets of the Milky Way, and we have no close analogue for them in our solar system, other than Uranus and Neptune. Every model of what these exoplanets are made of, how their atmospheres work, how their magnetic fields behave, and whether they could support life-friendly conditions, is based on assumptions about ice giant interiors derived primarily from our understanding of Uranus and Neptune. If that understanding is wrong, if Uranus is rock-dominated rather than ice-dominated, the chain of inference built on the ice giant template collapses. Consider the scale of this problem. The Kepler mission alone identified thousands of confirmed exoplanets, and the statistical analysis of that dataset revealed that sub-Neptune worlds are the most abundant type of planet around Sun-like stars. Roughly 30 to 50% of Sun-like stars host at least one planet in the sub-Neptune size range. This is the most common scenario in the galaxy, and our entire effort to understand all those worlds is being held hostage by a fundamental uncertainty about a planet in our own backyard. But now it's time to bring all this evidence, all these anomalies, all this wrongness together. This planet is not a world with a single interesting feature. This is a world whose entire physical character is built on violating the expectations that all other planets have taught us. So, what does this mean? Not just for Uranus, but for the very idea of a planet itself. A picture that will change. And now, it is time to stop and think. Because all this data, all these discoveries, all these wrongnesses bring us to one fundamental question. Is this just a story about Uranus? Or does it contain a deeper lesson that shakes our assumptions about our place in the universe? Because there is a silent assumption most people carry about the solar system. It runs so deep they never articulate it, never examine it, never realize it's there. The assumption is that we know this place, that the 8 planets orbiting our star are understood objects, that the remaining mysteries are details, footnotes, loose threads at the edges of an otherwise complete tapestry. We learned it in school. We've seen their pictures. The story, for the most part, has been told. But Uranus dismantles this assumption, layer by layer, because it doesn't have a single weird feature. Every planet has something unique. What makes Uranus different is that the weirdness isn't a feature. It is the architecture itself. And so, we confront the first and most fundamental contrast. the vast chasm between the place we thought we knew and how little we actually know. On one hand, we have our own solar system, our backyard, the planets we have mapped, used, modelled, years, and memorized the names of since childhood. A domain humanity has observed for thousands of years, writing myths about it. This is our cosmic home. And in this home, there is a giant planet 4 times wider than Earth, 14 times more massive, with 29 moons. But, on the other hand, stands the fact that we don't. Therefore, when we bring all these contrasts together, the known versus the unknown, the speed of discovery versus the duration of neglect, the dramatic versus the important, the physical reality versus the human narrative. The picture that emerges is not just of a strange planet, but also a reflection of ourselves. Uranus is a mirror for humanity. It reflects the limits of our attention. It reflects our tendency to mistake a first impression for a final judgment. The assumption that if something doesn't look interesting at first glance, it probably isn't interesting at all. And it reflects the cost of that assumption. A planet sitting in the dark for 40 years, waiting for someone to come back with better instruments and a longer attention span. This is a comparison that goes deeper than resource allocation. When Cassini arrived at Saturn in 2004, it completely transformed our understanding of the Saturn system. Juno did the same for Jupiter. Every flagship mission has returned results that forced a major revision of previous understanding. There is no reason to believe a Uranus mission would be any different. On the contrary, there is every reason to believe it would be precisely more transformative, because our starting knowledge is so much weaker. The unknown is not evenly distributed throughout the solar system. It is concentrated at Uranus. It is deep, dark, and waiting there. But beyond all these philosophical reflections, there is a more concrete place this story brings us. The next step, the future. Because our ability to answer the most fundamental questions about this planet is no longer just a dream. It is a possibility being planned, debated, and perhaps, within our lifetimes, becoming a reality. And that possibility promises more than just understanding a planet. It holds the potential to change the way we understand ourselves. Because the next great frontier may not be out there, but just beyond our own assumptions. Just beyond our own assumptions. And for that reason, we now face a deeper question. Because these possibilities, these future missions, bring with them not just a scientific, but an existential reality. This reality is the fundamental contrast between our action and the universe's unresponsiveness. On one hand, there is humanity's incredible capacity to act, to explore, and to understand. The 2022 Planetary Science and Astrobiology Decadal Survey, the document that sets NASA's scientific priorities for the next decade, ranked a Uranus orbiter and probe as the highest priority new flagship mission for the 2023 to 2032 period. Not Mars, not Europa, not Enceladus, but Uranus. This ranking was not a gesture of pity toward an overlooked world. It was a scientific judgment that the questions Uranus can answer are now among the most important in planetary science. This is a testament to our ability to plan, to allocate resources, and to imagine a journey of billions of kilometers. We are a species that can sit here, plan decades ahead, and consider building a spacecraft that will arrive when a child born today reaches adulthood. But, on the other hand, there is the absolute indifference of the universe to this effort. Uranus is unaware of our plans, our priorities, our decadal surveys. It does not care if we come or not. It will continue to spin as it has for billions of years. This is a tragic loneliness, because it shows that all our efforts, all our passions, all our intellectual energy are a signal sent out into a silent and unresponsive cosmos. We are beings in the vast ocean of existence, trying to create meaning for ourselves, waiting for an echo but hearing only silence. This is the fundamental truth of the human condition. We care, but the universe does not. But in this tragic silence lies the deepest beauty, because the universe's indifference does not make our actions meaningless. Quite the opposite. It makes them even more meaningful. If there is no purpose bestowed upon us by the universe, then it falls to us to create our own purpose. If meaning does not come from without, then we must derive meaning from within, from our own curiosity, our own desire to explore, our own need to understand. The act of sending a mission to Uranus, therefore, is not just about collecting data. It is an act of defiance against an indifferent universe. It is a way of saying, you may not have a purpose, but we do. It is the purest expression of the human spirit, the drive to create meaning in the midst of meaninglessness. You are a part of this act. Your life may be small and fleeting in the grand scheme. But your curiosity, your desire to learn, your ability to ask questions, is a fire lit against the silence of the universe. The Uranus mission is not just the project of a handful of scientists. It is a symbol of the collective curiosity of humanity, of which you are a part. And when that spacecraft launches one day, it will carry not just instruments, but also a part of you, a spark of your quest to understand. And this brings us to another internal contrast, the paradox between the technological power we possess and the fragility this power reveals. On one hand, since we have our incredible technological achievements, the Uranus orbiter and probe, Odysseus, if built, will be a marvel of human engineering. It is targeted to launch on a Falcon, heavy or equivalent launch vehicle. Receive a gravity assist at Jupiter, and arrive at Uranus around 2044. This mission would include an orbiter and an atmospheric probe. The probe would plunge into Uranus's atmosphere, providing the first in situ measurement of what an ice giant's atmosphere is actually made of. The orbiter would map the gravitational field with enough precision to break the interior composition degeneracy. This is a testament to how complex the tools we can create to unlock nature's secrets are. But, on the other hand, what this technology shows us is how delicate and unexpected planets can be. New models about Uranus's moons are the best example of this fragility. It is suggested that Ariel and Miranda may have experienced significant tidal heating in the past, and could potentially harbor subsurface liquid water even now. Ariel is one of the brightest and most geologically young moons, with surface features pointing to a relatively recent resurfacing. This is a stunning set of clues for a moon orbiting a planet most people assumed was geologically dead. This is a tragic awareness, because it suggests that worlds that could harbor life might be far more common than we thought, but also far more hidden and difficult to reach. Oceans may be hiding in darkness, under protective ice shells, billions of kilometers away from us. We have the technology to find them, but it takes generations to get there. This means our knowledge always runs one step ahead of our reach. But in this tragedy, there is also an extraordinary beauty, because it fuels the hope that the universe might be teeming with potential life. If an orbiter detects evidence of a subsurface ocean at Ariel or Miranda, it would mean that ocean worlds are not confined to the Jupiter and Saturn systems. They would extend into the ice giant realm, a region of the solar system never before explored in any meaningful depth. This would instantly expand the implications for habitability, for the distribution of liquid water in the cosmos, and for where we search for life. It would further strengthen the idea that we are not alone. At least in terms of biological potential, it shows that even the coldest or darkest corners of the universe can harbor the warmth and chemistry necessary for life to emerge. You are a part of this potential. You are a being made of liquid water, organic molecules, and energy from a star. A potential ocean on Ariel or Miranda is an echo of how common the fundamental components of your existence might be in the universe. It creates an invisible bond between you and the most distant, coldest worlds. And it reminds you how resilient, how creative, and in what unexpected places life can emerge. And this brings us to one final thought, one final contrast. This is the struggle between the comfort of our categories and the true complexity of nature. Because we divide the solar system into categories: rocky planets, gas giants, ice giants. These labels are useful shorthands, but they carry an implicit promise that the members of each category are broadly similar. But perhaps Uranus doesn't fit comfortably into any of these categories. It is not the exception that proves the rule. It is the entity that breaks the category itself. And this says something profound, not just about planets, but about the way we understand the world. Because perhaps the greatest barrier is not the distance of space or the limits of technology, but the limits of our own minds. Perhaps the greatest discovery is not finding a new world, but finding a new way to see worlds. Finding a new way to see worlds. And for this reason, we descend to one final philosophical layer. Because the greatest lesson Uranus teaches us is perhaps the endless dance between knowledge and uncertainty. On one hand, there is the power of the scientific method, our ability to observe, hypothesize, test, watch, and understand. The James Webb Space Telescope's mapping of Uranus's ionosphere is the latest example of this power, a structure that was only theoretical for 40 years. We can now observe directly. This is a triumph of knowledge. It is proof that human intellect can unravel even the most complex secrets of the universe. Every new data point, every new observation, is a candle lit in the darkness of ignorance. It is a force that fuels our faith in progress, our hope that our questions will eventually be answered. But on the other hand, there is the fact that every new answer inevitably begets more questions. Webb's ionosphere map gave us answers, but it also created new mysteries. Why is the upper atmosphere cooling? Why do the ion densities not match the models? How is the energy crisis resolved in this unique geometry? This is a tragic truth, because it shows that knowledge is not an ultimate destination, but a constantly expanding horizon. The more we learn, the more we realize we don't know. Every discovery is a new peak that only allows us to see more clearly how vast our ignorance is. This is a profound lesson in humility, meaning we may never reach a complete understanding, that the universe's secrets will always be one step ahead of us. But in this endless quest lies the greatest beauty, because if we had all the answers, there would be nothing left to discover. If the universe were completely understandable, there would be no reason for curiosity. Uncertainty is the engine of science. It is what pushes us forward, what encourages us to look deeper, to ask harder questions. This is a lesson that the journey is more important than the destination. What Uranus offers us is not a finished map, but a continent waiting to be explored. And that is a more exciting prospect than knowledge itself. You are a part of this dance. Your life is a journey between certainties and uncertainties. You find answers, but those answers give birth to new questions. Uranus teaches you to be at peace with this uncertainty, to see the unknown not as a threat, but as an adventure. It whispers to you that the greatest wisdom lies in admitting how little you know, and that admission is not the beginning of fear, but of wonder. And this brings us to perhaps the most practical contrast: the balance between short-term costs and long-term value. On one hand, there is the cost of a Uranus mission: billions of dollars, decades of planning and development, the labor of thousands of scientists and engineers. These resources could also be used to solve pressing problems on Earth. This is a tragic choice, because, and it shows that in a world of limited resources, there will always be a tension between our dream of reaching for the stars and our responsibilities on our own planet. Every dollar spent on space is a dollar not spent on Earth. This is a hard truth that shows the cost of scientific discovery is not just financial, but also has moral and ethical dimensions. It requires us to ask the question, why? Why should we go so far when there are so many problems to solve here? But against this cost, there is a long-term and hard-to-measure value. Because space exploration doesn't just produce data and technology, it produces perspective. Studying a world like Uranus reminds us how rare, how precious, and how fragile our own planet is. It makes us ask fundamental questions about our place in the universe, about our origins, about our potential future. It inspires. It motivates the next generation of scientists, engineers, thinkers. It allows humanity to unite around a common purpose, and that value cannot be squeezed into a budget line. It defines who we are as a species, what we value, and what we aspire to be. You cannot measure the value of the pale blue dot photograph taken by Cassini from Saturn in dollars. It created a shift in human consciousness. A Uranus mission has the same potential. You are a part of this value equation. The taxes you pay, the policies you support, the curiosity you instill in your children contribute to this great journey of discovery. Uranus reminds you that the best investments are not always the ones that provide an immediate return. Sometimes the greatest value lies in a spark of inspiration that echoes for generations. In a single image, a single idea that changes our view of the universe and ourselves forever. We know now that Uranus is not just a tilted planet. It is a riddle that shatters our assumptions, breaks our categories, and forces us to think deeper. It is a symbol of neglect and potential, of knowledge and uncertainty, of human narratives and cosmic reality. This long journey has taken us not just to the cold outer reaches of the solar system, but also to the limits of our own understanding. And now, as we bring all these pieces together, we see that this strange, wrong, yet captivating world has one final lesson for us. This lesson is perhaps the most important, because this lesson is not about how a planet works. This lesson is about how we as a species look, how we see, and most importantly, why we have been so blind to what has been in front of our eyes all this time. And this final thought brings us back to the very beginning of the story, to that simple, childish joke, because the truth behind that joke is not just funny, it is also profound and a little unsettling. We've seen how Uranus breaks the rules. But I didn't tell you that the flow of time is not an absolute rule either. Einstein's theory of relativity and the immense gravity of black holes can slow down time, stop it, and maybe even reverse it. On our next journey, we will explore the physics of the time machine. Are you ready to buy a ticket to the past?